Assalamualaikum and a very good morning to Madam. So today we are presenting our project entitled Traditional Image Processing and Machine Learning for Diabetic Retinopathy Stage Classification. So this is our group members, which are Nurul Asma binti Mak Fazil, which is me, Siti Aina Sofia binti Zali, Shazrina Sofia Sharazad, Mazatu Maisara binti Mansur, and Alwani binti Samri. For this presentation, each member is responsible for a different part of the project. So next. Diabetic retinopathy is one of the leading causes of blindness among diabetic patients. Early detection is important because it can help prevent permanent vision loss. However, manual screening of retinal fundus image requires experience of ophthalmologists, takes a long time, and may produce inconsistent results due to differences in human interpretation. Although deep learning can achieve high accuracy, it can usually requires large dataset and high computational power. Therefore, our project used traditional image processing and machine learning as a simpler, lighter, and more interpretable approach. So the first objective is to pre-process retinal fundus image to improve their quality. So the second objective is to extract meaningful features using traditional image processing method. And the third objective is to classify diabetic retinopathy into 5 severity stages using machine learning. And lastly, the system is evaluated using accuracy, precision, recall, and a confusion matrix. Okay, next. For the dataset, we use the balanced diabetic retinopathy dataset from Kaggle. It contains 5 classes: no DR, mild, moderate, severe, and proliferative DR. A total of 750 retinal images were used. For each class, 100 images were selected for training and 50 different images were used for testing. Therefore, the complete dataset consists of 500 training image and 250 testing image. The testing image were kept separate from the training image to avoid biased results and to ensure that the classifiers were evaluated using unseen data. Overall, this project aims to develop an automated system that can classify diabetic retinopathy severity using traditional image processing technique and machine learning method. That's all from me. I will pass to the next presenter. Thank you.
My name is Itana Sofia. I'm going to present about pre-processing and segmentation. So before any feature can be extracted, every retinal image in our dataset has to go through a pre-processing pipeline to improve its quality and make the important retinal structures easier to isolate. The first step is green channel extraction. Retinal images are captured in RGB, but the green channel specifically gives the best contrast between the retinal's blood vessels, lesions, and background tissue, so we use it instead of a plain grayscale conversion. Next, we apply a median filter, which removes small speckle noise from the image while still preserving the edges and shapes of important structures like vessels and lesions. After denoising, we apply contrast-limited adaptive histogram equalization, or CLAHE, which enhances local contrast in the image. This is important because lesions such as microaneurysm and hemorrhages can be very subtle, and CLAHE makes them stand out more clearly without over-amplifying noise the way a global contrast stretch would. Once the image is enhanced, we apply Os's method, which automatically computes a global threshold from the image histogram and converts the enhanced grayscale image into a binary image, separating potential regions from healthy tissue. Finally, we perform morphological opening, closing, and confident to clean up these binary masks. As a last cleanup step, we discard any connected components smaller than 50 pixels using area-based filtering, since these are too small to represent real lesions. On this slide, you can see two examples from our dataset, which the original green channel image on the left, moving through median filtering, CLAHE enhancement, and also thresholding in the middle, and arriving at the final segmented lesion map on the right. As you can see, the retinal structures become much clearer and more defined after processing. That said, we did notice that some very small or faint lesions may not always survive this pipeline, which is something that can affect feature extraction and classification later on. With the images properly segmented, I will now pass it over to my teammate to explain how we turn these segmented images into numerical features.
Assalamualaikum, my name is Shazrina Sofia, and I will be presenting step 3, which is the feature extraction. So after the images are segmented and cleaned during pre-processing, we still need to convert those images into numerical data that a machine learning model can actually process. And that is where feature extraction comes in. Rather than using deep learning, our project extracts 7 handcrafted features from every retinal image, then organized into 2 traditional image processing domains, which is color statistics and GLCM texture features. The first domain is color and statistical features. It is calculated directly from the enhanced grayscale pixel distributions. These are mean, variance, and skewness. Mean captures overall baseline brightness. Variance measures the spread of pixel intensity. variations, and squiness evaluates the asymmetry of the pixel intensity distributions. So together, these three values describe how bright, spread out, or lopsided the pixel values are, which helps us detect structural abnormalities like hemorrhages and acidics. The second domain is texture features, computed using the grayscale coherence matrix or GLCM to analyze spatial relationships between neighboring pixels. From the GLCM, we extract four key descriptors: contrast, which measures local intensity variations; correlation, which evaluates linear dependency between pixel pairs; energy, which measures texture uniformity; and homogeneity, which reflects how similar neighboring pixel values are. These four metrics capture fine retinal texture changes across different disease stages. Finally, all 7 handcrafted numerical values are concatenated into a single feature vector per image. This feature vector forms a structure 7-column matrix, yielding a 500 times 7 training matrix and 250 times 7 testing matrix, which serves as a direct numerical input for our classifier. So I will now hand over to the next presenter to explain how this feature matrix is classified. Thank you.
Thank you, Shazuna. My name is Maizatun Maisara, and I will present the next step, which is classification. In our project, we use the k-nearest neighbor or KNN algorithm. As shown on the slide, the model first uses 500 rebel training images, where each image is represented by its extracted features. Next, 250 unseen test images are used for classification. For each test image, KNN compares its extracted features with those of the training images and finds the k-nearest neighbors, which are the most similar images. The test image is then assigned to the class that appears most frequently among those neighbors. The classifier predicts one of the 5 diabetic retinopathy severity stages: no DR, mild, moderate, severe, and proliferative DR. After all the test images have been classified, the predicted labels are compared with the actual labels to evaluate the performance of the system. I will now pass the presentation to my teammate, who will explain the results.
My name is Alwani. Now I would like to properly evaluate our classification system. We use a confusion matrix along with 3 standard metrics: accuracy, precision, and recall. The confusion matrix compares the predicted class label against the actual class label across all the 250 test images. So we can see exactly which classes are being predicted correctly and which one are being confused with each other. Looking at our KNN results, the no DR class was a standout success. All 50 no DR images were classified correctly, giving us 100% precision and recall for that class. That makes sense, since healthy retina looks clearly different from disease one. However, the 4 disease classes told a different story. Mild had 21 correct prediction, moderate only 15, proliferative DR 14, and severe just 9 out of 50. Most of the errors happen between neighboring severity stages. For example, severe images were often mistaken for moderate or mild, which tell us that these classes share overlapping color, texture, and lesion characteristics that our current feature set struggles to separate. So in terms of overall numbers, our KNN classifier achieved an overall accuracy of 43.60% on the test set. Moderate had the lowest, which is 22.39%, while severe had the lowest recall at 18%. For comparison, we also trained an SVM classifier on the exact same feature. It achieved a slightly higher overall accuracy of 45.20%, although it showed a very similar pattern, strong on no DR, but still struggling to separate the 4 disease stages from one another. So, in conclusion, this project set out to build an automated diabetic retinopathy classification system using traditional image processing and machine learning, and we believe it succeeded the goal. Our pipeline, green channel extraction, CLAHE, enhancement, thresholding, and morphological refinement, reliability, isolates retinal lesion without needing any deep learning. Our 13 handcraft texture, statistical, and lesion-based feature carry enough information for 5-class KNN classification, and the system perfectly distinguishes healthy retinas from disease 1. The main limitation we identify is that the 4 disease severity stages, mild through proliferative DR, remain difficult to separate due to overlapping visual characteristics, and that is the clearest direction for future work, whether through richer feature, better classifier tuning, or eventually benchmarking against deep learning approaches, while still keeping the interpretability and advantage that traditional methods offer. Overall, we believe this system has a real potential to support ophthalmologists with faster, more consistent preliminary screening, and I guess that's all from us. Thank you for watching.